have our notes. Got some friends online. We got some stickers. We got a thumbs up. All right, so I think we are ready to get started. Unless anybody has any questions, we're going to go through section, let's put this over here. We're going to go through section 2.3. So if you remember, we are doing geometry, but it doesn't feel like math, right? Because we have been talking about inductive reasoning. So we kind of notice a pattern, right? And we've been talking about conditional statements. So if you are on or appear in, then you are a good geometry student. That would be our if-then statement, right? So if you are on appear in this morning, then you are a good geometry student. So if I would negate that, it would say, if you are not on appear in this morning, then you are not a good geometry student. For all of those that aren't here yet or are listening online. So we talked about conditional statements in the if-then form. So the if is the hypothesis and the then is the conclusion, right? And we can write the converse, the inverse, and the contrapositive of those. So let's do a really, really quick review of that. Does anybody have a good if-then they want to use this morning? You can type it in the chat if you do, or you can talk to me. Nobody's got it? Oh, can't hear anything. That's not good. All right, can you guys hear me or not? Kirsten can hear me. Does anybody have any tips? Okay. Hello, Sophia. Hey. Sophia, I want to come to your house. It always sounds like a party there. I love it. All right, so the person that can't hear anything, I am talking. Does anybody have any tips? Like, do you have to unmute anything? I'm not even sure who that is. All right. I'm not sure who that is. But we're going to go ahead and get started because I think we're 10 minutes in. I hope that whoever that is gets their technical issues fixed. I'm not trying to leave anybody behind. But yes, so let's do a quick review of conditional statements. So if then. So here's our if then. All right. If my computer let me type. If you are on appear in, then you are a good geometry student. So that would be my if-then statement, okay? If you are on appear in, then you are a good geometry student. I'm just totally making this up. This is, you know, you might not be on here for a specific reason and be listening later, or your speaker might be broken. But that's going to be my if-then statement. So if I wanted to write the converse of that, the converse is when we're going to switch the hypothesis and the conclusion. So the converse of my statement would be, I'm going to make it a little smaller so it fits on here. The converse would be, if you are a good geometry student, then you are in appear in. Make sense? We switch the hypothesis and the conclusion. Okay. If we wanted to write the inverse, oh man, the inverse actually means we're going to negate both the hypotheses. So the inverse would say, if you are not on appear in, then you are not a good geometry student. That's the inverse of my original conditional statement. And then the contrapositive, if you remember, means we're going to switch and negate both. So if you are not a good geometry student, then you are not on appear. Oh man, I wanted to stretch that out. All right, so everybody remember that from Monday where I picked on Mackenzie and Olivia for their coffee? It's all in good fun, ladies and gentlemen. All in good fun, right? All right. And these statements are true. If you're not on appear in today for some reason, you still could be a good geometry student. Doesn't doom you for life. All right. So we're going to go over 2-3 today, which is another, we talked about inductive reasoning. Now we're going to talk about deductive reasoning. Okay. So let's pull this out and talk about what deductive reasoning is. All right, so deductive reasoning. So if you remember, inductive reasoning means you're using your observations to kind of make a rule. So I forget what my deductive reasoning was, or my inductive reasoning was. I think it was something like, oh, everyone likes appear in better than anything else. I think it was the example we used, right? I'm just using what feedback that I get, what I observe, and I'm making a guess. Deductive reasoning is different because the definition of deductive reasoning is that we are going to use facts, definitions, accepted properties, and the laws of logic to form a logical argument. So if you remember back in 2-1, we talked about inductive reasoning. Okay, so inductive reasoning is you're going to use patterns, example, observations. You're kind of going to use it's kind of like the hands-on knowledge, right? You're going to use all that. Deductive reason is like, nope, we're going to use the facts. We're going to use definitions. We're going to use properties. We're going to use all those to form a logical argument. Okay, so inductive is more like the touchy-feely. I mean, it's still based off of things, but it's more observation patterns, right? And we even have, with inductive reasoning, we have counterexamples to disprove our inductive reasoning. Deductive reasoning is much more like, well, I know based off of this definition and this fact that this is true, and so I'm going to make that true. All right? Does that make sense, the difference between the two? Yep. All right. Awesome. All right. So we're going to talk about two different laws. Okay. The first one is called the law of detachment. All right. So it says if P to Q is a true conditional statement and P is true, then the fill in the blank is that Q is true. So let's unpack this a little bit. So this has conditional statement, right? Conditional statement is our if then statement, right? If, like, for example, if we said, let's do a really easy one. Let's do a really easy conditional statement. So if the traffic light is red, then you stop. Okay? So this would be our conditional statement. It is a true conditional statement, right? For those of you that are drivers or going to be drivers soon, I hope that you believe this is true. If the traffic light is red, then you stop your car. Stop your car, right? So what this says is that if you get into a situation and you say, oh, the traffic light is red, then it's also true that you must stop. Okay? So it basically says if this statement is true, then if the first condition is the if part is true, then the second then part is true. So that's the law of detachment. So we'll practice some with that. Actually, let's skip to example 3 where we have the law of detachment, and I'll pull that up here. Okay. So let's talk about the law of detachment here. Copy. Yep, if the first part true, then the second part is true, exactly. Move that down. Oh, we need to make this bigger. Hold on. Gotta use my paint skills here. Oh man, I messed that up. All right, well, we're just gonna have to do this. So let's see if the argument is valid or not. So letter A says, if Roger gets a part-time job, then he will buy a new bicycle. So this is our true statement here, okay? If Roger gets a part-time job, then he will buy a new bicycle, okay? So then the next part says, Roger buys a bicycle. So Roger got a part-time job. So is that necessarily true? The statement is, the conditional statement is, if Roger gets a part-time job, then he will buy a new bicycle. But we actually have him, he buys a new bicycle. Does that mean that he got a part-time job? No, right? Exactly. That does not mean it's true. The law of detachment doesn't work the other way. So basically it's saying, so we can say that this argument is not a valid argument, right? If it said Roger got a part-time job, then we could say he will buy a new bicycle. All right, so this is not valid. No. All right. So let's try another logical argument. Feel like you're in logic class. If two angles are vertical angles, then they are congruent. All right, so do you remember what vertical angles are? Anybody? Vertical angles are when you have, yep, when you have two lines that intersect, right? Then the angles that are formed by the intersection, the opposite angles are congruent, right? So if two angles are vertical angles, then they are congruent. And then we have angle 1 and angle 2 are vertical angles. So angle 1 and angle 2 are congruent. Is that a valid, is that argument valid based off the law of detachment? I got one yep. Yes, that is true, right? Because it meets our criteria. So angle 1 and angle 2 are vertical angles. So we have the if part checked off, right? If that's true, then they are congruent. So angle 1 and angle 2 are congruent because it meets our properties. So we would say yes. This is a logical argument. All right, state whether the following argument is valid. If two adjacent angles form a straight angle, then the angles are supplementary. Okay, so if basically what they're saying is if two adjacent angles form a straight angle, so if they basically do this, then they are supplementary. And remember, supplementary means, if I can write supplementary means 180 degrees, right? Okay. Angle 1 and angle 2 are supplementary. So can I conclude that they are adjacent? No, right? Nah. I think that's Kirsten, isn't it? Yes. Kirsten says nah. And I agree with her, right? Because what they're doing is yeah. The argument or the conditional statements is if the two adjacent angles form a straight angle, right? And so they're giving us basically the conclusion, not the hypothesis. So this is not a valid argument. Does that make sense? Does anybody feel like they need some more examples? Or are you able to see? Basically, if you use the conditional statement exactly like it says, then it is a valid argument. And if you flip things around, then it's not a valid argument anymore. Okay. So then we have another deductive reasoning law, and that's called the law of, now I have to say this every time, the law of syllogism. Is that fun to say or what? The law of syllogism. And I totally had to look that up the first time. All right, so this says if P goes to Q and Q goes to R are true conditional statements, then P, oh, I can't make an arrow. P goes to R. Should be a little arrow there. All right, so let's talk about some examples with this. So basically, if I have, let's see. If you are in geometry, then you are in high school. Okay, so that's one true conditional statement. Okay. Actually, let's see. You are in let's see. Okay. If you're in geometry, then you're in high school. If you are in high school, you are awesome. If I can spell awesome right. Okay. So here's my two true statements. You could maybe argue with the second one, but not in my class. Everyone in my class is awesome that's in high school, right? So this is just an example of two, if we would say these are two true conditional statements, right? If you're in geometry, then you're in high school. And if you're in high school, then you're awesome. So the law of syllogism basically says that this is like our P. If you are in geometry, then you are in high school. If you're in high school, you are awesome. So then I can say, if you are in geometry, then you are awesome. This should say then right here. All right, because I can use the law of syllogism that says if one statement is true and the next statement is true and the conclusion of one shares the hypothesis of the next, then you can combine them together. Does that make sense? So a very geeky, mathy one would be like, if I'm just trying to think. If x equals 1, then x plus 1 equals 2. Okay. And if x plus 1 equals 2, then I don't know. It is raining. These are kind of totally made up. But if those are both true, then I could say if x equals 1, then it is raining. Because they share the same hypothesis or the same conclusion and hypothesis. Does that make sense how the law of syllogism works? I think this one's kind of fun. This is more fun than the other one. You know. And you guys are all probably thinking, this is math? This is kind of weird. This is geometry, right? All right, so now we have a list of statements here that are all true. Write some conditional statements that can be made from the following true statements using the law of syllogism. Okay? So we have a lot of different statements here. We have number 1 says, if a cat is the largest of all cats, then it can weigh 650 pounds. If a cat lives in a pride, then it is a lion. If a cat weighs 650 pounds, then it is a tiger. If the cat is a tiger, then it hunts alone. If the cat is a lion, it can weigh 400 pounds. Sounds like a bunch of facts here, right? So what are some statements that we can make based off the law of syllogism? Syllogism, yeah. Okay. And there's more than one answer to this. So the first one I see, the first one that pops out to me, is if we use statement 3 and statement 4 together. Okay, so if a cat weighs 650 pounds, then it is a tiger. If the cat is a tiger, it hunts alone. So the conclusion of 3 shares the hypothesis of 4. So we could combine 3 and 4 together to say, if a cat, oh, yellow is hard to see, sorry. If a cat weighs 650 pounds, then it hunts alone. Alone. My awesome typing skills. Can you see how you can combine those together? They share that they're both true. They share the conclusion and hypothesis. Who can see another one? Which two can we combine together? There we go. So what about statement 2 and 5? If a cat lives in a pride, then it is a lion. If a cat is a lion, it can weigh 400 pounds. So if a cat lives in a pride, then it can weigh 400 pounds. What about 1 and 3? If a cat is the largest of all cats, it can weigh 650 pounds. If a cat weighs 650 pounds, it is a tiger. So we can combine 1 and 3 together, 1 and 3, and we get, If a cat is the largest of all cats, then it is a tiger. And really, if we really, really, really wanted to get fancy, could we combine 1, 3, and 4 together? So if a cat is the largest of all cats, then it can weigh 650 pounds. If a cat weighs 650 pounds, it is a tiger. If a cat is a tiger, then it hunts alone. So we could combine 1, 3, and 4 together and say, if a cat is the largest of all cats, then it hunts alone. I really want to say along. That's how we would use the law of syllogism. And it's just fun to say, right? Syllogism. Any questions about that? I think it's a pretty easy little section. Quiet. It's quiet today. You guys are quiet. Okay, well, I'm going to go ahead and do just a little bit of 2.4 because there's a lot of fill in the blanks, so it's easy for me to do online, and that takes a lot of time in class. So if you have your notes, pull them out so we can add in what we have for 2.4, because that's it for 2.3. Pretty easy little section, okay? 2.4, all of a sudden, look at this. We have all these new postulates. Aren't you excited? Does anybody remember what a postulate is? Yeah, ew, right? So a postulate is basically a rule that everybody in geometry just basically accepts as true, not explains as true. Okay. So we are going to talk about, and remember we have 4 postulates that we talked about before, but it's basically just a rule that is accepted without proof. And some of these you should probably have heard of before, but let's just go ahead and fill in the blanks since I have my nice words up here, okay? So postulate number 5 says, through any 2 points there exists exactly one, and the fill in the blank is line. All right, so if anybody, you guys should have all taken algebra before, so you should probably have heard of this before. All right, so this says, through any 2 points, there exists exactly one line. So if I have, somebody else can't hear. Can you hear now, Mackenzie? Don't fail us now, appear in. Can't fail us, right? Mackenzie, if you, here, I guess I have to type to her. Maybe log out and back in. All right. All right, so the postulate 5 says, through any 2 points, there exists exactly one line. So basically this says, if you have a point here and a point here, if you have 2 points, Any 2 points. There's only one line that goes through those 2 points. There's no other way that you can draw a line that would go through exactly those 2 points. Okay? So that statement is true. We just accept it. Any 2 points, they're exactly one line. I think you guys probably know that from algebra, right? Heard that before? Maybe? Okay. Postulate 6 is kind of the opposite. It is a line contains at least 2 points. All right. So this is kind of the opposite. You have a line. If I can draw a line. You have a line. And in order to have a line, you at least have to have 2 points on that line. Okay. Postulate 7 says, if 2 lines intersect, then their intersection is a... So if 2 lines intersect, where they intersect at a... Anyone have a guess? At 1 point. When you have 2 lines, they intersect, intersect at exactly 1 point. All right. Postulate 8 says, through any 3 non-collinear points. This is exciting stuff, guys. There exists exactly 1 plane. So if you remember 3 non-collinear. So if I drew 3 points here, this is for number 8. 8's going to be in green here. If I can do this right. Okay. 8's going to be in green. No, maybe. There we go. 8's going to be in green. So we have a point here, a point here. So right now those are linear. If I drew a point out here, that would be collinear. We want 3 non-collinear points. So I have 3 non-collinear points. Through any 3 non-collinear points, there exists exactly 1 plane. So remember, a plane is in 2 dimensions, not just a line. Okay. And then on the flip side, a plane contains at least 3 non-collinear points. Okay. Postulate 10 says, if 2 points lie in a plane, then the line containing them lies on a plane. Okay. All right, so postulate 10 says, if 2 points lie on a plane, so right here we have 2 points are lying on our plane, then the line connecting them, the line connecting them also lies on a plane. So the orange line is on the green plane. Okay. And then the last postulate says, if 2 planes intersect each other, so you have a piece of paper going this way and a piece of paper going this way. Okay. Where they hit each other, they don't intersect at just a point. When 2 planes intersect, their intersection is at a line. Okay. So do all of those postulates make sense? I think they're all rules we've talked about before, but we're just going to make it more official. Everybody still here? Still alive. All right. It's not too terrible, right? All right. Good deal. All right. So let's just do one or two examples, and then again on Monday, we'll probably go over these again so they kind of stick in your brain. Okay? With your postulates, you have this picture here. It says, example 1, state the postulate illustrated by the diagram. So if we have 3 points, then, and these 3 points are collinear or non-collinear? Non-collinear, right? They're not in a line. So if we have 3 non-collinear points, then those 3 non-collinear points are on a plane, right? This is an example of a plane. So what postulate would this represent? I say postulate 8, right? Through any 3 non-collinear points, there exists exactly one plane. Everybody agree? You see that? Pretty easy, right? All right. Example 2 says, use the diagram to write examples of postulate 9 and 11. So we should refer back to what 9 and 11 are, right? And figure out what we have. Postulate 9 says a plane contains at least 3 non-collinear points. Okay? So if I look here at my picture, plane, let's see, plane Q contains at least 3 non-collinear points. What 3 non-collinear points does Q contain? It contains V, Y, and W. Right? What about plane P? Does it plane P contain 3 non-collinear points right now? They don't have 3 non-collinear points labeled, right? They just have X and Y on plane P. So we couldn't show the postulate for plane P, but it probably does have 3 non-collinear points. It's just not labeled. All right, and postulate 11 says the intersection of a plane P and plane Q is, so we've got our gray plane Q, and P is our other plane. So where do they intersect at? They intersect at a line, right? And they intersect at line B. So that is the funness that is 2.4 in all of our postulates. I think that's where I'm gonna wrap up today. I'm gonna save the other examples for Monday, so we'll go through these again on Monday just to make sure they stick in your brain. I know they seem super easy, but they're gonna be the basis for how we prove other things to be true. So remember how we just learned about deductive reasoning? We're gonna use these postulates to do deductive reasoning. So we'll say, if, two planes intersect, then their intersection is a line. But you guys are all looking forward to that when we get to do that, right? Yes. Can't wait. Awesome. All right. That is it for today. So we will pick back up with 2.4 and continue on Monday. Let me know if you guys have any questions about homework, test, any of that stuff. And have a great day. Sorry for those that had technical issues too. Will we have to memorize all the postulates? That is a good question. So if you look at the back of that, you guys, that has all of the theorems, The theorems actually have the postulates on the back page. So they're there. Oh, bummer. Yeah, so they're on the back page. What I would recommend, I'm actually glad you asked that, is that when you get to that back page, and remind me on Monday to do this with you guys, we'll actually draw some little pictures to go along with each of the postulates on your back page, so you have those for reference. Which sections did we go over? We did, we reviewed 2.2, we did 2.3, and we did part of 2.4. Yes, we will finish up 2.4 on Monday. You can probably do 2.4, honestly. If you want to go ahead, if you have time, you can probably get through 2.4. But we'll just review it again because I want to go through it twice to make sure everybody gets it. All right, guys. That's it. Have a great day. Talk to you later. See ya.